Hello fellow problem solvers. So today we're going to be doing a problem from the 2008 IMO, problem number 1. I suggest you try this geometry problem out for a minimum of 30 minutes, ideally an hour to an hour and a half, but not more than 2.5 hours. If on the other hand you'd like to go along with us, I suggest you give it a go for the next 15 minutes. And now without further ado, let's begin. So this is what we have. We have an orthocenter, the midpoints of the sides BC, AC, AB, and circles with centers in the midpoints and radii, like the distance from the midpoint to the orthocenter. And they intersect these lines at A1, A2, B1, B2, so C1 and C2. And we need to prove that all these 6 points, A1, A2, B1, B2, C1, C2, lie on the same circle. So now, how will we go about doing this? What are like some of the first things that you would do here? So for me personally, the first thing that comes to mind as soon as I see this is, well, wait, can I just like do power of point? Can I do AC, A2, CA1? Like, can I calculate this? Like, what do I need to calculate CA2 times CA1? And the thing is, the only thing I need is A0H. And can I calculate that? Well, yes, I can. If the perpendicular here is D, then I can calculate this. I can calculate this, so I have the square of this, which means I have this as well. And given that, I can calculate all of these distances and prove that these points are concyclic. And now here, I would give you 10 minutes to see if you would like to do that. And the calculations become this, something like this, where you get that this is equal to cosine beta cosine gamma times BC minus cosine beta cosine gamma times 2r. And now to have CA1 times CA2 be equal to CB1 times CB2, just by analogy. Mind you, what were we doing? We were C and A1, A2. So this will be equal to, by analogy, this is going to be cosine gamma cosine alpha AC minus cosine alpha cosine gamma times 2r. And we must prove that these two things are equal. And how will we prove that? Well, cosine gammas cancel out. We have the cosine alpha times, let's do cosine alpha AC minus cosine alpha squared times cosine gamma times 2r needs to be equal to cosine of beta times BC minus cosine of beta squared cosine gamma times 2r. Like, it's a complicated expression, and now how are we going to solve this? I invite you, if you still want to continue doing this, to pause for another 5 minutes and try to solve it. And here's how you do. And for me, frankly, this is just way too difficult. I am not going to go down this route. For me, this is like when I get confused with like the sines and cosines, I'm like, let's get back to the original diagram and see if there's a better way to look at this. That's okay, mind you. Like, this is okay to like be okay with not following through on a thing and try to explore something else. And I'll come back to this if I can't find another way. But luckily for me, there is a different thing to look at. So thinking about like, what would solving it backwards, I need these for it to be concyclic. Okay, say they're concyclic. And I have A1, A2, H, B1, B2, and H. Like, if these are concyclic, then the intersection of these two circles is on CH. So now that's enough to prove. And what would that mean? That would mean that there's a point on CH that's such that A0, that point is equal to A0H, and B0, that point is equal to B0H. So now, what's the intersection with this circle and CH? Let's call this point, I don't know, P. And now what do we have? We have this is equal to this. Is there anything interesting about this point? I invite you to pause for 5-10 minutes and figure it out. And the answer is yes, but not quite. Because, like, mind you, this right here is at 90 because A0, B0 is parallel to AB and CH is perpendicular to AB, so it's perpendicular to this. So it means if we reflect H around A0, B0, we will get this point P that's equidistant, that has such that A has the same distance to it and H, and B has the same distance to it and H. So that means that this point is on both of these circles, And now we just have power of points, which is much nicer, which we have C1, B1. We have this is equal to CH times CP, and this is equal to CB1 times CB2. And now we've proved that these four are concyclic, and also these four are concyclic, and these four are concyclic. And now with this, I invite you to pause for 10 minutes and figure out what would you do next. Have you finished the problem? And here's the next step. So if you thought that finished the problem, you're wrong. And the reason you're wrong is because we could have this sort of situation. C1, C2, and where is it? A1, A2 are concyclic, C1, C2, B1, B2 are concyclic, and all of these are concyclic, but they don't all lie on the same circle. So that is not enough. So what we've done just now, showing that all of these points, well, quadruplets actually, lie on the same circle, does not show that all of them together lie on the same circle. And now the question is, how are we going to do that? Now here's a good diagram. And now with the diagram, the question is, what is enough for us to now show to make sure that all of these lie on that same circle? Well, the answer is really, and here's where I wanted you to stop for 5 minutes if you haven't done so. And the thing is, what is the center of this circle around these 4 points? Well, it's the intersection of this perpendicular, which is the perpendicular of A1, A2 goes to A0, and this perpendicular bisector. Well, what is that? That is O. So we have O is the center of this circle, and it's the center of this circle and of this circle. And now we're done with the problem. Now, because O is the center of this circle, we have OA1 is equal to OA2 is equal to OB1 is OB2. And then from these 4 points, we have OB1 is OB2 is OC1 is OC2. And now because O is equidistant from all 6 of these points, that means all 6 of these points lie on the same circle. Now, this finishes out the problem. But there was a different way we could have come to this. And that is looking at it backwards. It's saying okay, these 6 points must lie on the circle. What is its center? Well, its center has to be O. Just like solving it backward, you figure out that the center has to be O. And now what's enough to prove? Well, it's enough to prove that OA1 is the same as OB1. And what do we need to do? Well, we need to calculate OA1. What is OA1? Well, OA1 is equal to what? The square of OA1, say, is equal to OA0 plus A0A1 squared. And this is OA0 squared plus A0 H squared. And we need to prove that this does not depend, this is the same for B0 and C0. Now, how do we do that? Well, we have this and this. And now, if you know a particular lemma, this becomes pretty quickly, you'll see what you need to do is if you take the midpoint here, if you know a lemma that says that AH is twice the size of OA0, that's a lemma, you can prove it by similarity. And now what do you have? If you take the midpoint here, call this point S, I don't think I've used S. Then we have what? We have this is a parallelogram because this is parallel to this and this is equal to this. And now what do we have? We have this squared plus this squared. So these are the sum of squares in a parallelogram, and they are equal to, this is a little diagram will help here. So the sum of the squares of the sides, this squared plus this squared, is equal to the sum of the squares of the diagonals, I believe, over 2 if I'm not mistaken. And we can show this quite quickly. And the way we show it is by putting down this. Now I know this is alpha, so these are congruent because this is equal to this. Now call this x, call this h, call this a, call this x, h. You have the sum of these 2 sides is going to be x plus a squared plus x squared plus h squared, the sum of these 2 squares. Now the sum of the squares of the diagonals, this diagonal is so let's do one by one. Where's this? Okay, we have this diagonal, a squared plus h squared, and then we have this big diagonal, which is h squared plus 2x plus a squared, question mark. Did I sum anything wrong? Oh, maybe divided by, oh yes, so this over 2 will be equal to this. I saw like I have 4xa, I have 2xa, and a squared twice, yes, I have x going 2 times here, 4 times here. Yes, so we know this is equal to the sum of the squares of the diagonals, which is a0s squared plus oh squared over 2. And now the thing is, oh squared is a constant, and we need to prove that a0s squared is a constant. But if you know that s, c0, b0, a0 all lie in the same circle, the Euler circle of the triangle, this just goes to show it's like useful to know these little tidbits about the triangles in general. And if you know this, then you know these lie in the same circle, and also the feet of the perpendiculars lie in the same circle as well. So a0s is actually the diameter of that circle. So that means all of this is equal. So it means this is equal to b0s, like call it t squared, like here, call the point t, b0t squared plus oh squared over 2. And then we are done. That's how we'll show that OA1 squared is OB1 squared, and similarly it follows for C. And this was our problem. It's a cool little thing where having background knowledge helps, and there's this like little bit of a trap, so to speak, that just because you prove that all 4 of these, actually all quadruplets, not all quadruplets, but these 4, and these 4 lie in the same circle does not mean that all of them lie in the same circle. And that's a trap to be just aware of. So this solves our problem, and as always, thanks for problem solving.